In this lesson, we want to figure out ways to optimize the size of our code. When we talk of the caches, you may think its performance is set by the hardware and that nothing can be done by software to improve its performance. You are right, nothing can be done in software to make the caches faster, but we can reduce the slow interactions with the cache, which will greatly improve overall performance. We are going to learn to reduce slow cache interactions, also known as dynamic loads and stores, through intelligent register allocation. Reduction in dynamic number of loads and stores reduces cache activity and reduces energy consumption. Improvement in energy consumption and performance are most desirable, and binaries for non-embedded domains can be recompiled towards the embedded domains via advanced compiler techniques that we are going to look at in this lesson. So students, having seen how a basic register allocator works, graph coloring based allocator, and the other techniques that come in with it, such as splitting of live ranges and so on, which help it to become more and more effective. Now we are ready to tackle some embedded compiler optimization problems from this lecture onwards, and we are going to focus on how register allocation first helps to improve the code for embedded systems in terms of performance, energy, as well as code size. So the first lecture is devoted towards that now, which helps us cache energy consumption reduction using clever register allocation. So as you know, caches is where the data is mostly found when it is brought into the processor. Many of these load stores go and hit the cache and get the data from there and bring it inside the processor, and then the processor does the operation on this particular data. Whenever these load stores are going to the cache, there's a lot of dynamic activity which happens in the cache, and that's a source of a lot of energy consumption. What kind of dynamic activity occurs here? The dynamic activity could involve lookups, matching of tags, locating the data, and actually transferring the data as well. And all these activities increase the memory energy, and it's a good idea to reduce this dynamic activity. So in this piece of work that we are going to see here, we are going to use feedback-directed post-pass register reallocation solution. What does that mean? A post-pass means we have register allocation already done, but it is not really geared towards solving this particular problem. So what we have is really a binary or an assembly code generated in which some kind of register allocation is done, but it is not done and which is not geared towards solving this cache energy consumption problem. So we are going to do a reallocation here. To some extent, we are going to reassign these registers in this assembly code so that we can optimize the cache energy. And again, the goal is clear here, to reduce the dynamic load store count of the program. Remember here, the dynamic load store count means the total number of loads and stores that go into the cache and which contribute to this dynamic activity of the cache to match the tags, to locate things, to transfer the data, and so on. And so the key idea here is to reduce the load stores going to the caches by utilizing the information of allocated registers and to reallocate those so that the dynamic number of load stores is reduced. Let us revisit the problem of register allocation. One assumption may be that the values are all held in memory and then on demand they are loaded into registers and stored back into the memory. And this assumes that the home location of all the values is memory. However, in almost all the modern processors and especially the embedded processors, we do not undertake this type of an assumption. On the other hand, we assume that the home location of the variables is going to be in registers, and each of the values is residing in a symbolic register. And then our goal, as we saw through the previous lecture on register allocation, is to map these infinite symbolic registers to finite number of physical registers. And in such process, some of the variables may not get a register and will have to be spilled to the memory and restored back. Even in approaches such as splitting, this will happen, and that is the approach which we focus on in this particular lecture as the starting point. So first we are going to quickly review how a graph coloring register allocator really works. Again, it builds an interference graph after constructing webs and so on. Next thing it does is to color the interference graph. So these problems being hard and taking an exponential time, many times heuristics algorithms are introduced, as you know, which involve optimistic or pessimistic assumptions, and they will try to color the graph in linear time. If the coloring doesn't happen well, obviously we are going to have spill variables, or we are out of registers, we cannot fit all those values. There will be spills that are generated here. So spills could be because of three different reasons. One is because they are native load stores. Some values are unsafe to be kept in registers, so that's why we have load stores going there. The second is because we have heuristic algorithms, so it is a non-optimal solution, which is leading to lots of load stores. And the third one may be simply a genuine problem that we are just too few registers, and so the values just cannot fit in there, and we have to store and load some values out of memory. As you know, in this particular process, we also split live ranges to give registers for a part of the range when we cannot give it to the whole range. So students, having understood what coalescing really means, now let us understand if it is helpful in certain situations. What we have here is a simple example, and the question here is coalescing helpful for this type of an interference graph? Note here that P and Q are Mu-related nodes. In other words, a register-to-register move is needed here because these two could get different registers. These nodes, if coalesced into one live range, which means they will be allocated to a single register, can get rid of such a move. And then the question is, should we go ahead and do the coalescing? Is it going to be profitable or is it not going to be profitable? It will save a move, that is the profit side of it, but if we do the coalescing, something else might happen, which may not be a good idea. So the question is coalescing helpful here? Please mark your answers as yes or no. Go ahead and mark your answers now. And the answer here is no, coalescing is not really helpful in this particular situation. Now let us really understand why coalescing is not really helpful here. For the original graph, as you can see here, we could color it with two colors, red and green. We could give P a red, M a green, N a red again, and Q a green. And that's how this particular graph is colorable with two registers. In other words, there is no spill here for this particular graph. Now let us see what happens if we coalesce these two nodes or merge them together. What we get is now this kind of a graph in which we have P and Q merged together as one node, and that one range now, unified range, interferes both with M and N. In other words, we form this type of an interference graph here. Now let us look at the coloring aspect of this particular graph. As you can easily see here, this graph is a clique of size equal to 3, in which each node is interfering with every other node, and therefore we need here 3 colors. If we give M a red color, N a green color, we have no other color left here because we have only 2 colors available, and therefore the coalesce node P and Q has to be spilled. If we coalesce P and Q, it will save us a move, but it will cost us a spill, lots of spills for this particular live range, and therefore it is not worth coalescing this P and Q here. So again, what is the reason? Coalesce node P and Q form a clique of size 3, and it spills on 2 registers, and therefore coalescing, although it saves a move, is not worth it because it costs us spills. The previous graph coloring based register allocation we saw was during the code generation. Now what we are going to do is, after the code is generated, after the registers are allocated, there may be still suboptimal opportunities which we are going to correct through this, and that's why it is called as post pass. So it is a post code generation pass. So here is the problem. Because we use heuristics, or because of the inherent way the code is there in terms of live ranges and so on, a number of dead and or unused registers could be still available, and we want to be able to use these registers to do something useful using them, putting some part of live ranges in them. This is especially true when the number of registers available is small, such as 16 or 8 as against 32, because such a sparsity of registers leaves a lot of dead ranges in place. So the problem of splitting is one of trying to improve the code efficiency, and it does not sometimes fill these registers which are dead or unused with the actual ranges that could be fit into it, and therefore these ranges remain unassigned, and on the other hand we have some dead and unused registers. Finally, what is the difference between dead versus unused register? A dead register is one which has already been given to a live range, the live range has ended, and now another live range is assigned into that register further down in the control flow graph. So in other words, a dead register does not carry a value between the last use point of the previous range and the first definition point of the ensuing range. As against that, what is an unused register? An unused register is the one, imagine a long live range, and it is carrying a live value, but for a large part of that range it is unused. And a typical register allocator would try to use some kind of a splitting, but unfortunately, in some cases, the cost of splitting was a little too high and so on. So splitting was rejected, and this particular register is now unoccupied for a large part of that live range, and that is the definition of an unused register. So again, note the differences between a dead register and an unused register, as I mentioned. Now we are going to couple that with something else. In a typical register allocator, as we know, we are doing some static estimation of biasing the register allocator towards those values which are inside the loop nest over the values which are outside those loop nests. But in this particular case, since our goal is on reducing dynamic activities in the cache, we are going to do some profiling. So this is a profile-based approach in which we are going to execute the code, find out which of the paths are hot and which of the paths are cold. After doing profiling, we find that typically 30% of the code is hot. In other words, it's very frequently executed. Whereas 70% of the code is cold, is rarely executed or infrequently executed. And what we are going to do is redo the allocation to bias it towards the hot code. Again, if we bias it towards the hot code, we are going to see that the dynamic activities in the cache will go down, and that is our intention for saving energy. We are going to do this reallocation again just within the function call or procedure calls. Again, doing whole program reallocation is expensive, difficult, and is also not quite effective. The solution that we are going to see here is a fast solution. The reason being that this solution could be just in time before the program is loaded and executed. So that's why compilation time is important here. We are going to do very simple analysis and focus only on reallocation in hot regions to minimize the dynamic number of load stores. Let us look at another example here in which we have an interference and we have availability of register for partial ranges here. So again, what we have here is different ranges which are spanning through a simple control flow graph here. V4 spanning from here to here, V5 spanning from here to there, V1 spanning from here to here, V2 going from here to here, and then finally we have a long range V3 which spans across all these different ranges. As you can see here, if we end up giving a register to a long range V3, it is going to jeopardize the other ranges from getting registers. So what we'll do here is we'll determine the interference graph and figure out that this long range in fact is the reason for interference for the other ranges. And as you can see here, V3 is at the heart of all the interference here. We'll figure that out. I will not get into how. And then we will undertake the splitting of V3 and allocate a part of this V3 as V3 dash into register R1, which we have not really given out earlier. So you can see that in this particular way, a part of the range can be covered. Of course, this needs a sophisticated analysis to determine that V3 is the culprit and V3 could be split in the proper way and that the registers could be given out in a particular way. So in our approach, we are going to undertake a different approach. Rather than doing this in the static times, we are going to get some dynamic profiling information, determine the hot and cold paths, and weigh the splitting in such a way that we are going to eliminate lots and lots of load stores on those hot paths. So here is the overall framework for this particular approach. We start with the program assembly code or a binary. Then we do some analysis. we build the control flow graphs at the binary level, we instrument them, and then we run a profiler and generate profiling data. This tells us which paths are hot and which are not. Now, on the other hand, what we do is we build this control flow graph and we find out what are the spill variables and where. We combine this hot data and we use analysis to figure out what are the dead registers and what are the unused registers. So this is one of the critical analysis that we undertake, which I mentioned earlier. Dead registers are again those in which one range has ended, the register is free now, and the second range is not loaded yet. Whereas unused means it does contain a live value, but for a very long region, there are no uses of that value, and so we can cut up the range, throw the value in the memory, and use that register for a long time and then restore it. Now, using this particular information of dead and unused registers and hot and cold paths, we are going to undertake the register reallocation. And so therefore, we'll have an improved binary. So let us now look at some details of how this is done in terms of the register reallocation, and that's going to be our focus for the remainder of this discussion. We first identify hot regions, and we are going to build a weighted bipartite graph. What is this graph going to show us? On one hand, it is going to show us what are dead and unused registers in different program regions. On the other hand, it is going to show us what are spilled ranges. And we are going to try to do a matching of these two. We are going to do the benefit and cost analysis for this matching, and then we are going to think about how to generate the compensation code once we decide to save and restore in these dead and unused registers different values. So this is the overall framework which details, this is the heart of all the work that this particular phase does in terms of register reallocation. And we are going to look at certain details of this now. So one of the key things that we are going to look at here is the dead and unused registers, how to identify them, the hot regions, and then the weighted bipartite matching of those two. And we will do the unused or dead register allocation there as a result of this. So students, having seen the concepts of what exactly is a dead register, now let us understand if we can find if a register is dead at a certain program point through a simple example. I have shown you a simple control flow graph with certain loads, stores, and uses of registers. And the question that has been asked to you is, at program point A, is register V1 dead? And then the next question is, at program point B, is register V1 dead as shown in the control flow graph? Please mark your answers as true or false for each of these questions. Please go ahead and mark your answers now. And the answers are, let us consider the program point A, and the question was, the register V1 is dead here. The answer is, this statement is true. Let us understand why. You can see that the register V1 is loaded here, is used here, but then stored back to the memory over here, and there is no use of this V1 from this point onwards till a new value is loaded over here. So in this interval or in this range, there is no use of V1 and the value in it is dead, and therefore V1 is dead. That statement is correct or true here. Let us look at the second question. At program point B, is V1 dead here as per this control flow graph? And the answer in this particular case is false. Let us understand why that is the case. So V1 is not dead here. Why is that? Because V1 is loaded here, a new value is put in V1, and that value exists here. Somebody is going to use that value over here, and then that value is stored back at this particular point. So the value resides in that register which is going to be stored back later, and that's why V1 is busy here or has a live value in it in this particular interval, and that's why V1 is not dead. Now let's look at the dead unused register information analysis, how it is done. So as I mentioned earlier, a dead register is the one which does not carry a live range at a given program point. So how do we find it? We find it through a backward data flow equation, and the analysis is exactly same to the live variable analysis that we seen in earlier reading assignment. The details of this analysis is also in the paper which is assigned along with the slide for reading. And what it does is it keeps track of, at a certain program point, are there any further uses of this particular register. If there aren't, then that register is dead. In short, the deadness is very easily characterized, that the live ranges have ended prior to the current basic block due to the stores, and new values are loaded in this particular register downhill in the control flow graph through the loads. On the other hand, we also have unused registers. What is an unused register? A register is unused in a particular basic block if it is neither defined nor used in a given block, but it is live across that particular block. In other words, it has a definition which is sitting in the control flow graph before this program point, and it has a use sitting in the control flow graph after this particular program point. Now, the analysis that we saw earlier for deadness might also detect unused registers, but on the other hand, we may have some other unused registers which are sitting inside a live range. And so, if that is the case, if there is a long unused part of the live range, then what we could do is we could put a store before this load, store the value into a memory, free up this register, allocate it to some other live range which has not gotten a register, and then restore it through another load at the point of its use. Here is a simple example of a dead register. You can see that this is the last use point of V1, and then V1 is redefined into another variable over here, and we'll get a new register from here. From this point to that point, V1 is dead. Similarly, as far as this basic block is concerned, we can see there are no definitions nor any uses of V2. The earlier use was over here. So this V2 is unused in this particular part of the region, and that's why V2 will be an unused register here. So students, we have seen what is exactly meant by a compensation code. These are the load stores that are inserted to free a live range, to be able to use their registers and so on. So let us now test our understanding here through a quiz. Which of the following statements are true? Mark all the ones that are true. The first statement is, in general, more compensation code is needed to use a dead register than unused register. Second statement is, after our optimization of post-pass reallocation, the total number of static load stores might increase, but the dynamic ones during execution should decrease. Please go ahead and mark all those statements that are true. Please mark your answers now. Now let's take a look at answers. So the first statement is, in general, more compensation code is needed to use a dead register than unused register. This statement is false. Why? Because dead register does not have any value in it, so we don't need to carry out any stores or restoration of that value. However, an unused register has a live value resident in it, and we first need to store it, and then at the end of the range, we need to restore it back. So we need these boundary load stores because of this reason, and so more compensation code is needed for unused registers than dead registers. Let us now look at the second statement. After our optimization, the total number of static load stores might increase, but the dynamic ones should decrease. This statement is true because this is our goal here. We might insert boundary load stores for freeing a register, especially for unused registers, and then use that particular freed register for allocating to a range so that we decrease the dynamic load stores of a spilled range. So the dynamic load stores are going to go down and the static ones might go up. And you will see that later on in our results, this is really the case. So now, having understood how to find dead and unused registers, let's focus on hot region identification. Again, what we want to do is, on this hot region, we want to remove every possible spill if we can, and maybe at the cost of generating some spills in the cold region. And the idea here being, that way we'll reduce the dynamic cache activity. So the simplest way to find out an execution frequency of a basic block is to do a profiling and find out average dynamic execution frequency if it is greater than a certain threshold. And a typical threshold could be the average execution frequency of all the basic blocks. So in other words, we'll bias it for all those blocks which are above this threshold, select them as hot blocks and the others as cold blocks. Typically, this average value tends to be shifting towards or biased towards very high frequently executing blocks, and so it serves as a great way to get rid of almost 70% of the code, focusing on the 30% of the hot code. Now remember, our goal is to find out the maximal hot regions. So far, in the previous step, we just found out hot basic blocks, but now we got to merge the adjacent hot basic blocks and form large regions of hot code. So typical properties of hot regions are they are convex. In other words, typically a control flow goes into a hot region, stays into that hot region, and then branches out of the hot region into a cold basic blocks. So many hot regions are separated by cold basic blocks. And then, therefore, the hot regions are disjoint, and we can carry out the register reallocation independently for these hot regions. In other words, one hot region doesn't impact the register allocation of another hot region, and so these decisions can be decoupled. Now that's a very important property for register reallocation. That means it's a very local problem. So students, as we mentioned earlier, we have dead or unused registers on one hand, and lots of values which are not assigned to registers on the other hand, which are present in large regions, which are hot regions. And if we manage to assign them to each other, then we have managed to get rid of all those spills and therefore reduce the dynamic counts. And we carry this particular process through what we call as weighted bipartite graph matching. So you all know what a bipartite graph is. It has two partitions, a set of nodes on one side and another set of nodes on the other side, and they are connected through edges. That structure of a graph is called as a bipartite graph. In our case, one of the bipartitions is a set of spilled variables, that is, those variables which could not get registers in specific regions of CFG or control flow graph. On the other, we have dead or unused registers which could hold certain values. And then, if a variable and a register could be matched, or if we can assign a register to a variable, then there is an edge that is present. And we do this on a basic block by basic block manner. That is, inside each of the basic blocks, if we find a variable that has uses and an available register, which is a dead or an unused register, we put an edge to indicate that they could be together. Finally, we weigh these edges by putting a weight on it. And what is that weight? That weight is the number of dynamic spills that could be avoided. For example, there is a variable in a particular basic block, and we find a register for it. The execution frequency of that basic block will tell us how many dynamic loads will be avoided if we were to give a register to that variable. And so using this type of a representation, we carry out the register reallocation. In order to carry out the reallocation, we have to compute what is called as overall benefit. First is the benefit of reassignment, that is the number of dynamic spills that we can get rid of. But it is not as easy as that, because we also want to worry about the compensation code. What is a compensation code? Remember that in case of dead registers, we simply need to just load a value and then use the value from that register. So we just need one load. However, in case of unused register, we need to store that live range into its home location, and we have store sitting at the top, and then we need to restore it at the bottom because those values need to get back in registers, and so we have loads coming at the bottom of this unused range. And so we pay some price by adding some load stores in either case, and that is called as the compensation code cost. We try out different matchings, and they could have different kinds of costs and also different kinds of benefits. And the goal of doing this is to maximize the overall benefit. Let us look at a couple of examples to get this concept a little bit more clearly and to get an idea of the issues involved here. So what we have here is a bipartite graph. The variables V1 and V2 are the spilled variables which are there in basic block B5. On the other hand, in the same basic block B5, we have either an unused or a dead register available, which is R1 here. since both of these variables are in the same basic block, we have the same dynamic benefit of avoiding the spills. Let us say, in this case, a value of 10,000 is the frequency of execution. Now it so turns out that maybe V1 was referenced twice and V2 was referenced only once within that block, in which case V1's benefit would be 20,000, twice of that of V1. So that would be for that kind of an example. In this example, however, we have exact same benefit for V1 and V2 in this particular basic block. And we have a choice of allocating that register R1 either to V1 or to V2, but not both. And that is shown through this simple example here. Now, if it is a choice of putting compensation code to relieve register R1, that would be a cost which will have to be subtracted from these to find out if there is any benefit left here. And that would be the case for R1 being unused register in this block. We'll have to store the value which is there in R1 into its home location and restore it. If it's a dead register, however, we'll just have to load the value straight into that register and we'll incur a load of that particular value as its cost. So using this benefit and that cost, a decision will be taken if it is worthwhile giving a register to one or the other variable or to neither one of them. Again, remember, the moment we give out register to one of them, it is not available to the other, and that's why this problem is the matching problem, which is in a classic problem of bipartite graph matching. Now the bipartite graph can get complex because now we are considering the whole region, not just a single variable in a single basic block or multiple variables in a single basic block. So in this example, we have two basic blocks which are adjacent to each other, B5 and B6. First basic block has V1 as a spill variable. Second basic block has V3 as the second spill variable. In a basic block B6, however, we had register which is available for R1. We do not have this register available in any other block, and we have another register available R2 in basic block B6. So now it's a question of how to match these registers which are available to these different variables, and those are represented using these benefits. However, just like in the other example, we need to analyze the cost benefit and overall benefit that is remaining in the presence of a cost and then take care of this matching problem. So you can see that the matching problem is complex because different registers are available for removing the spills in different basic blocks. There are different costs associated with the compensation code, and certainly there are different benefits that are associated with different variables that whose spill could be removed. And so this problem has to be solved in a very sophisticated manner. So as you can see here, from the perspective analysis, we need to really worry about what is the cost of compensation code or what is the penalty that is involved here. The benefits are very easy to compute because it is the number of dynamic load stores which will be removed. But calculating the compensation code in terms of its costs can be a little bit tricky. So the first thing we need to do is to choose an analysis units. So what we do here is we choose the edges which are incident on the same variable and the same register, and then we combine such edges in adjacent basic blocks. Why are we trying to combine such edges between the adjacent basic blocks? Well, the main idea here is to avoid the compensation code. So for example, if we give the same register to the same variable on two adjacent basic blocks, we don't need to do anything in terms of compensation code, and that avoids that particular cost. So that is what we are trying to look at first. So the compensation code analysis starts by considering three regions. The first is, of course, the current region, which is the set of basic blocks and corresponding edges in the analysis unit, which need to be extended to their adjacent counterparts. We extend the current region to the predecessor region by removing or combining those edges as we talked about on the previous slide. And finally, we do the same by extending the region to the successor basic block and continue this particular process to determine as large a region as possible where we don't need any compensation code whatsoever. After computing the largest compensation code free region, our next goal is to find out the compensation code costs at the boundaries of such region. We calculate this cost in terms of the load stores that we need to place. So there could be a load which could be placed in the current region, or there could be a store which could be placed in the current region, or we might have to place a load in the predecessor region, or we might have to place a store in the successor. What is going on here is this compensation code is trying to put a store to free a particular register and using load to get the right value in the register, and that's why these costs are being calculated here. So having seen now how to calculate the benefits and how to calculate the compensation code costs, which are really important for unused register allocation, because the final benefit is subtraction of the cost from the benefit. Now let's see how to write a simple algorithm for carrying out this register allocation. So such an algorithm has two parts. One is to identify the register allocation region for unused registers. And as I mentioned earlier, we'll merge the adjacent basic blocks and find out the largest possible region that we could have so that the same unused register can be used for that particular region. And the second part is how to now actually calculate the registers in terms of their allocation once we have found all these regions. Remember that these regions could overlap with each other, and so we had to guide the allocation from region 1 to region 2 by prioritizing the allocation in region 1 over the region 2. So how do we carry out this prioritization? We use a simple heuristic, which is the greedy heuristic. We find the region with the maximum benefit and start giving out the registers in those regions. We delete then the unused register regions that have common basic blocks with it, so they are not allocated in the other regions. And we keep repeating this process. In other words, we are trying to be greedy here in terms of getting those basic blocks in a region that gives its maximum benefit, carrying out register allocation within that region so that those blocks are taken care and the registers are also used in an efficient way, in the maximal way, and then we go to the next region which has the next higher benefit, and we keep doing this particular process by repeating this again and again. So students, now let's test our knowledge of unused registers through a simple quiz. I have shown you a simple control flow graph, and we have here a question whether for this particular control flow graph and when the registers are being used the way they are, is V1 an unused register at program point A? Please write your answer in terms of true or false. Go ahead and mark your answer now. And the correct answer in this particular case is that at program point A, V1 is indeed an unused register. Let us see why. Let's look at what is going on with V1 here. So we are loading a new value into V1 through this load. We are using this value over here. So there is a use of this V1 in this particular place. Now we enter this loop and execute this loop many times. You can see that there is no use of V1 here. And then later on, as we exit the loop, again there is a use of V1 here, and finally the value in V1 is stored. So there are uses of V1 here. There are uses of V1 here, but there are no uses in this particular area. And so V1 is unused during the execution of this loop, and that's why this statement is correct. As mentioned earlier, the unused register allocation has one more facet attached to it in terms of compensation code. We need to store the original value to the memory to free up a register here. We need to load the variable into this unused register during the region. Finally, we need to store this variable which we allocated this register back to memory at the end of this region, and then restore the original value to the unused register. So these kinds of load stores form the compensation code for unused registers. Remember, the compensation code for dead register is much simpler. because we need to just have this load which loads the original value into a dead register and then have a store at the end of this region which stores that value back to the memory. So these two first and the last parts are not there in such a case. I have here a few statements. Please mark those statements which are true with a check mark. The first statement: if the code were to be generated by a perfect register allocator, we'll have no post-pass register allocation opportunities since there will be no dead or unused registers available for reducing spills. Is this true or false? Second, more dead registers are likely to be found in code generated by a register allocator which is not equipped with live range splitting than the one equipped with live range splitting. Is this true or false? The next sentence is more unused registers are likely to be found in code generated by a register allocator which is not equipped with live range splitting than the one equipped with live range splitting. And finally, typical hot regions of a program include loops. Please go ahead and mark your answers now. So let us consider the first statement. If the code were to be generated by a perfect register allocator, we'll have no post-pass register allocation opportunities since there will be no dead or unused registers available for reducing spills. Is this true or false? The statement is false. Even if it is a perfect register allocator, remember that we may have gaps in allocation and there could be potentially some dead or unused registers available for reducing spills. Second statement: more dead registers are likely to be found in code generated by a register allocator which is not equipped with live range splitting than the one equipped with live range splitting. This statement is true because live range splitting tries to take care of sub-ranges rather than trying to decide on a complete range, and therefore it utilizes the registers better. Third statement: more unused registers are likely to be found in code generated by a register allocator which is not equipped with live range splitting than the one used with live range splitting. This statement is also true because live range splitting allows you to take advantage of the gaps in register allocation and therefore leaves less number of unused registers than the one which does not do live range splitting. And finally, the last statement: typical hot regions of the program include loops. Absolutely. What are the hot regions? The ones which execute with high frequency, and loops are those which execute with high frequency. Finally, let's look at certain experiments where this was carried out. So it has a x86 type of an architecture. It had general purpose registers that are present in x86 ISA. ESP and EBP were the stack pointer and a frame pointer registers which were not, of course, available for any allocation. This whole research was built into the MarkSwift infrastructure. This was an open source compiler which was doing machine dependent optimizations. And in particular, it had an excellent support for profiling, because remember, for doing profile driven analysis, we need to insert instrumentation into the program, count the basic block execution frequencies, and so on. And that support was excellent in this compiler. Finally, for the results that are reported later, we had George and Appel's algorithm, which was doing Chaitin style simplification steps with brick style allocation steps. In other words, the algorithm was spilling a node beforehand and then trying to use the stack for coloring the rest, and so on. And the benchmark that we used was Spec 2000 and MediaBench. Please refer to the details of all this in the instructor's manual. There is a paper which is published, which is there in that instructor's manual, which gives all these details. So here are some results in terms of the hot and cold blocks and the number of spills which were there in the original code and the ones which were removed by our framework, and so on. So as you can see here, much lesser amount of code is hot code and a lot more code is a cold code in each of these benchmarks. You can see that it is almost 20 times, many times, and so on. So a lot of hot code is concentrated in a few basic blocks, which is the good news because these are the blocks we need to concentrate on to get rid of the dynamic load stores and to reduce the memory activity. Now you can see that the spills which were there were removed from these hot regions because of two reasons. One is using the dead registers and second is unused registers. And this is the static spills which are removed. There were originally 701 spills, but they were removed 36 of them were removed by the dead registers here. In case of another benchmark, 28 of them were removed and 7 were removed in terms of the parser benchmark. Remember, these are the static number of load stores which are present in those many blocks. As compared to dead registers, you can see that unused registers have not been very useful in removing these kind of load stores. The main reason here is the cost of compensation code. Remember, the unused registers need the original value which is present in a given register to be first stored and then reloaded, and that cost outweighs benefits many times, and that's why sometimes there is no code which is removed in terms of the spills by the unused registers. So here is a summary of the results which we talked on the previous slide. The number of overall blocks which are hot are small. Size of hot regions is also small. Majority of the execution time of a program is spent in a small region. The spills removed by dead registers are much larger. The spill removed by unused registers are small. Now here is a summary of the time spent by the compiler in carrying out the reallocation, because remember that we cannot have an exorbitantly large compilation time, and we try to use the heuristic method of calculating the cost benefit and for doing the bipartite matching, mainly to keep the compilation time low. You can see that in most cases the compilation time has been low. In some cases the compilation has been a little bit slower, mainly because it has to analyze a lot of things, and these are large benchmarks. So now here are the results for static and dynamic spills which are removed. Please refer to the instruction notes and the downloadable there for the complete set of results and their discussion. The first column gives the comparison of the original versus the modified code in terms of the static number of load stores. You can see that in one case there has been actually an increase in the static number of load stores. Can you think of why? Remember that after we perform our reallocation, there may be a compensation code that is added to the original one. Some load stores are removed, but some others are added because of the compensation code, and that's why this number of static load stores could go up. In many cases, however, the compensation code that was added was not much, and the static number of load stores have in fact gone down. The real story, however, is in terms of the dynamic number of load stores that are executed by the benchmark. The goal here being to reduce that number, because that number really tells us how much energy is being spent in the cache. So in the original program, we had a large number which was reduced after the reallocation. The overall benefit of dynamic spill reduction has been significant, ranging from almost 27% to 10% for these partial results. Now let's look at the breakdown of the dynamic load stores that were removed. First, how many were removed by the dead, and second, how many were removed by the unused. You can see here that the benefit is again much higher for dead. For example, here there are no unused which has any benefit, but the dead ones have all the benefit. And many other cases, the dead registers are in fact reducing the dynamic number of load stores. Again, this is because for unused registers, a lot of benefit is outweighed by the compensation code, and so the benefit of removing those stores and loads by using unused registers is very limited. Many times that optimization was not undertaken. Now here is a take on the performance for all these different benchmarks in terms of number of cycles, and what we have here is the execution time pretty much has remained the same after doing the register reallocation. You may ask why. Again, the main reason for this optimization was to reduce the dynamic count of load stores, but in terms of the cycle counts or the amount of time each benchmark takes to execute, this time has not been reduced because the x86 is a dynamically pipelined architecture, and reordering of the load stores at runtime hides their latency, and so the benefits are not much in terms of reducing the latency or the cycle counts here. On a different architecture which doesn't hide the latency by dynamically reordering the instructions in the hardware, which is quite typical of the embedded processors, we could potentially see more benefit in terms of cycle counts as well, and that's something which could be evaluated on in-order architectures or processors where such benefits of removing dynamic load stores translate into the latency reduction or the less number of cycle counts of the program. Finally, let us look at the energy consumption. How is the energy consumption computed? It is computed by using the activity count of the cache and the total duration of the activity, which is the execution time of the program. By multiplying this two quantities, we are able to find out the energy. By using the energy models which are described in the downloadable, we were able to compute this energy for the unmodified benchmarks and for the modified benchmark after we carried out these optimizations. You can see that we have substantial benefits in terms of energy reduction as shown over here, mainly because the number of dynamic load stores have been reduced. Although the execution times have been pretty much remaining the same, the reduction in the cache activity causes the reduction in energy here. And so to conclude, in this first research artifact on embedded system, what we saw was by cleverly redoing the register allocation at the binary level, which is what we call as post-pass, we are able to reduce the cache activity, although we are not able to reduce the total execution time that much because all those latencies are already hidden and are used by the reordering of instructions and so on. Due to the reduction in the dynamic activities, there is overall energy reduction, which is really important for embedded processors. In this lesson, we discussed a feedback-directed post-pass register reallocation framework that is based on profiling information. We utilize dead and unused registers and reduce dynamic load store counts and improve data cache power consumption. We saw static code size increases, but we saw dynamic spills decreased. Overall, energy delay product was improved by 8.5%.